In this video, we're going to talk about two things: real-time system scheduling and the dining philosopher's problem. In real-time system scheduling, we're not going to talk about specific algorithms to do it, but we are going to talk about whether we can schedule in real time or not. For example, let's suppose a process occurs every time. So a process runs every 100 milliseconds and lasts 50 milliseconds. So we can look at that setup, and we can say, okay, well, we have CPU time on the top, we have what's called a period on the bottom, and that's equal to 1/2, and that's less than 1. We don't want the denominator to exceed the numerator. Now, let's add a process and see what happens. We don't want the period to exceed the CPU, that is. Okay, so we have our existing process, 50 over 100, and let's add on some other process, 25 over 100. So the new process takes 25 milliseconds, and it also runs every 100 milliseconds. That's equal to 3/4, and that's still less than 1. So is it schedulable? Schedulable? Yes. Schedulable. And the answer is yes. And then obviously in the first case it was also yes. Now let's add yet another process, a third. So we have our original, our second one, and let's say our third takes 20 milliseconds, but it runs every 60 milliseconds. Well, that's equal to 1/2 plus 1/4 plus 1/3, which turns out to be greater than 1, so it is not schedulable. Now that doesn't mean that if a set of processes is schedulable, that doesn't necessarily mean that it's all going to work out hunky-dory and beautifully. Maybe two processes need to run at the same time, and so we still have some issues there. But what we can say is that if a set of processes is not schedulable, then there's absolutely no way we can run in a real-time environment with these processes. Now, we have hard real-time systems, and in those, we cannot miss deadlines. And we also have soft real-time. And in soft, it's okay to miss an occasional deadline. Okay, so that's scheduling in a real-time system. Let's talk about the dining philosopher's problem. I'm going to bring up a figure here from the book. It is figure 245. The dining philosopher's problem. We have, in this example of it, we have 5 philosophers, each with a plate of food in front of them. A philosopher does two things. A philosopher thinks and a philosopher eats. And so we have 5 philosophers. To eat, they need both forks. So a philosopher might take the left fork and then take the right fork and then eat. Here's the problem. What if all 5 philosophers take the left fork? And then they go to take the right fork, but the right fork isn't there. The philosopher next to them has it. So they're going to wait for the right fork. But the problem is, none of them can eat. None of them is going to give up the left fork. And so they are deadlocked. They can't do anything. Let's just say deadlock. Okay, so we can fix it by take left fork, left. If the right is not available, put the left fork back, and then try again. Take the left fork, look to see if the right's available, and so on. Now, what if all 5 take the left fork? Then they all put the left fork back down. Then they all take the left fork. Then they all put the left fork down. So this can cause starvation. They're still doing something, but they're never actually able to eat. Okay, so let's take the left, put the right, put it back, and then wait a random amount of time. Does that work? Yes, that generally solves the problem, but many applications need to be deterministic. Now, before I show you the solution, you may have been looking at this thinking, how often is that going to happen? Why is this even an issue? And sure, maybe it won't happen very often, but are you willing to stake a multi-billion-dollar satellite on this never happening? So in many cases, we really need to have a solution to this. So I'm going to bring up figure 247 from the book. Which is the solution to the dining philosopher's problem. And looks about right. Ooh, you'd think I'd learn how to do that. Okay, here's the pseudocode for the solution. Let's be philosopher I. So I'm philosopher I come in, and forever, I loop forever. I first think, then I take the forks, then I eat, then I put the forks back. Now, and then I come back and I think again. Now let's suppose I think, and then I come to take the forks. So let's come down to take the forks. So it's this function here, and first I enter the critical region by calling down on the shared mutex. I set my state to hungry. I'm hungry. And so then I call this test function. This test function is the critical piece. If I'm hungry, I'm hungry. We'll see why we check in a minute. And neither of my neighbors is eating, then I can eat. And I'm going to call up on my own personal semaphore. So my own personal semaphore was 0. I'll call up on it, and now it's 1. I exit out of test. I can come back here, I exit the critical region, and I call down on that semaphore I just called up on, I return from take forks, and I eat. And everything's happy. I put my forks back, I come back, and I think. Now this time, let's say I think, then I come to take forks, I enter the critical region, I set my state to hungry, I call test, I come in, yep, hungry. But let's suppose one of my neighbors is eating. So I do not set my state to eating, and I do not call up on that semaphore. I just return from test. Now I come back from test, I exit the critical region, and I call down on my own personal semaphore. Now recall that we did not call up on that semaphore. The semaphore is still 0. And so when I call down on it, I block. And I block until someone wakes me up, until that semaphore gets set to 1. So I'm blocked. Now, what do I know about one of my neighbors? One of my neighbors is eating. So my neighbor finishes eating and puts the forks back. So let's go look at put forks. Put forks, enter the critical region. Now I'm thinking. And then the beautiful thing. My neighbor calls test on me. I come down to test. Yes, in fact, I am hungry. In other cases, when test is called on me, I may not be hungry, in which case I don't do anything. But in this case, I am hungry. Let's say my neighbors are not eating. So I set myself to eating, and up is called on that semaphore. The semaphore is now 1, and I was here blocked. But now the semaphore is 1, and down can return. Changes it from 1 to 0, returns, and I can come up and I can eat. And that is the solution to the dining philosopher's problem.